Imagine, for a moment, two structures so large that light itself needs more than 1 billion years just to cross from one end to the other, drifting toward each other through the dark, and finally meeting. What would that even look like? Would there be a flash you could see from across the universe? A shockwave that rippled through the fabric of space itself? A sound if sound could somehow exist in a vacuum? It's a tempting image, the kind of cosmic collision that feels like it belongs in a science fiction film. But the real answer, once you start digging into what the largest objects in the universe actually are, and what colliding really means at that scale, turns out to be stranger, subtler, and in some ways even more astonishing than any explosion Hollywood could dream up. To even begin answering the question, we first have to agree on what counts as the largest object in the universe. That's not as obvious as it sounds. Space isn't empty and uniform, scattered randomly with galaxies like sprinkles on a cake. It's woven into a vast structure scientists call the cosmic web, a scaffolding of filaments, walls, and empty voids that stretches across the observable universe. Galaxies aren't spread evenly through this web. They clump into groups, groups gather into clusters, and clusters remarkably link up into even bigger associations called superclusters. And in the last couple of years, astronomers have pushed the boundaries of just how big these structures can get. In February 2025, a team led by astrophysicist Hans Boehringer announced the discovery of something extraordinary, a structure so immense they named it Quipu, after the knotted cords the Inca used to record numbers and stories. Quipu is essentially a giant cluster of galaxy clusters, stretching approximately 1.3 billion light-years long, more than 13,000 times the length of our own Milky Way, and containing roughly 200 quadrillion solar masses of material. To put that mass in perspective, that's about 200,000 times heavier than our entire galaxy. And Quipu wasn't alone. The same survey identified 4 other colossal superstructures nearby, including the long-famous Shapley supercluster. And together, these 5 structures encompass roughly 30% of all galaxies, 45% of all galaxy clusters, and a quarter of all matter within a huge swath of the nearby universe. When you hear a number like that, it's worth pausing. A handful of structures, threading through space like the veins of a leaf, contain a meaningful fraction of everything we can see in our cosmic neighborhood. So here's a natural question. If Quipu and structures like it are the largest things we know of, then surely the ultimate cosmic collision would involve 2 of these titans slamming together. 2 Quipus, so to speak, crashing across space in the grandest collision imaginable. But this is where the story takes its first surprising turn, because superclusters like Quipu are not, in the way we usually mean it, single objects at all. They're not held together by their own gravity in a tight, self-contained way, the way a solar system or even a galaxy is. Instead, they're loose, sprawling arrangements, collections of galaxy clusters that happen to be gravitationally attracted to one another to some degree, but which are also caught up in the overall expansion of the universe itself. And that expansion changes everything. Since the late 1990s, astronomers have known that the universe isn't just expanding, it's expanding at an accelerating rate, driven by the mysterious force we call dark energy. On the scale of a supercluster, gravity is fighting a losing battle against that expansion. Individual galaxy clusters within Quipu might slowly drift closer to their nearest neighbors over cosmic time, clumping together in a patient gravitational dance that plays out over many billions of years. But most of the supercluster as a whole is not destined to collapse inward and collide with anything. It's more like burning embers scattered from a fire, some sparks landing near each other and merging, most of them drifting farther and farther apart into the dark, carried by the ever-widening gulf of space itself. In fact, one of the open questions astronomers are still puzzling over is why we even see such regular repeating patterns of superclusters at all, since the standard model of cosmology doesn't fully explain the neat, almost rhythmic spacing between them. So if the very largest structures in the universe are too loosely bound to truly collide as single entities, we need to zoom in one level to find where the real cosmic violence happens. And that brings us to galaxy clusters, which are, in a very real sense, the largest objects in the universe that are actually held together by their own gravity into cohesive, unified structures. Unlike superclusters, galaxy clusters are true gravitationally bound systems. Dense knots of hundreds or even thousands of galaxies, all swimming together in a shared gravitational well, embedded in enormous quantities of hot gas and, if the standard model of cosmology is correct, staggering amounts of invisible dark matter. And these do collide. In fact, when they do, the results are described by scientists in almost reverent terms. Consider a galaxy cluster nicknamed El Gordo, Spanish for the fat one. located roughly 7 billion light years away, meaning we're seeing it as it looked when the universe was less than half its current age. El Gordo has a total mass of around 3 million billion suns, making it one of the most massive clusters ever found at such a great distance. And crucially, it isn't one cluster, it's two, caught in the act of a titanic collision, two enormous swarms of galaxies that slammed into each other at speeds of several million miles per hour. Researchers studying El Gordo have described mergers like this as, quite simply, the most energetic events in the universe since the Big Bang itself. Moments when incredible amounts of matter and dark matter collide at incredible speeds. The energy released in a collision like this is almost impossible to put into everyday terms, but scientists estimate the total collisional energy involved can reach somewhere in the range of 10 to the 63rd or even 10 to the 64th ergs, a number so large it barely means anything until you realize it dwarfs the combined output of every star that has ever existed. But here's where it gets genuinely fascinating. Because a collision between two galaxy clusters doesn't look anything like what you might picture when you hear the word collision. Each cluster is really three things layered on top of each other. The galaxies themselves, which are relatively small and spread thin, a much larger reservoir of superheated gas that fills the space between the galaxies and actually contains most of the ordinary atomic matter in the cluster. And finally, an enormous, invisible halo of dark matter that provides most of the cluster's gravitational muscle, if the leading theory is correct. When two clusters crash into each other, these three components behave in wildly different ways. The galaxies themselves, despite being flung through each other's territory at millions of miles per hour, essentially never touch. This sounds impossible until you remember just how empty galaxies really are. The distance between individual stars within a galaxy is so vast that even when two whole clusters of galaxies interpenetrate, the individual galaxies pass by one another like ghosts, sliding through the gaps with almost no direct stellar collisions at all. It's a strange but telling reminder that even the densest concentrations of matter we know of are, on a star-by-star basis, almost entirely empty space. The hot gas, however, tells a completely different story. Unlike the galaxies, the gas clouds within each cluster are diffuse and continuous, filling the space between galaxies like an invisible ocean. When two clusters collide, these gas clouds smash directly into each other, experiencing tremendous friction and drag. The gas slows down dramatically, compresses, and heats to staggering. Temperatures, sometimes tens of millions of degrees, hot enough to blaze brightly in X-rays that telescopes like NASA's Chandra Observatory can detect from billions of light years away. This collision essentially strips the gas away from the galaxies that were originally carrying it, leaving it lagging behind, pooled in the middle of the wreckage, while the galaxies themselves sail on ahead, unimpeded. And then there's the dark matter, which behaves in the strangest way of all. As far as astronomers can tell, dark matter interacts with almost nothing, not even with itself, beyond the pull of gravity. So during a cluster collision, the dark matter halos of each cluster pass through one another almost completely unaffected, just like the galaxies, sailing straight through without slowing down or heating up the way the gas does. This creates a bizarre and beautiful signature. After the collision, you end up with the visible galaxies and the invisible dark matter moving ahead together, while the hot, glowing gas, which actually makes up most of the ordinary matter, gets left behind in the middle. This exact signature is what made a similar system called the Bullet Cluster so famous. The Bullet Cluster is the aftermath of a galaxy cluster collision that occurred 3.8 billion years ago, located roughly 3.7 billion light years away, and it represents very strong evidence for the existence of dark matter. By using a technique called gravitational lensing, essentially measuring how the collision's gravity bends and distorts the light from galaxies far behind it, astronomers were able to map out where the mass in the cluster actually was. And they found that most of that mass was in two ghostly blobs, offset from the glowing X-ray gas, tracing the same paths as the galaxies rather than the gas. For nearly 2 decades, this has stood as one of the most compelling pieces of evidence that dark matter exists and behaves essentially as a collisionless substance, sailing through cosmic collisions like a crowd of people walking straight through a wall of fog. It's worth noting, in the spirit of staying current, that science never really stops questioning even its most celebrated results. Just this year, researchers using fresh data from the James Webb Space Telescope revisited the Bullet Cluster and found that while their observations remain consistent with the standard dark matter explanation, they're also consistent with an alternative model that doesn't require dark matter at all. And if dark matter is present, it may exist in smaller quantities than previously thought. This doesn't overturn decades of evidence in one stroke, but it's a healthy reminder that even our best cosmic detective stories are still open investigations, refined and challenged as our tools get sharper. So if you want to picture the most violent, genuinely destructive collision the universe can offer, a clash between two galaxy clusters is about as close as you can get. An unstoppable smashing together of matter on a scale that dwarfs entire galaxies, releasing more energy than almost anything else since the birth of the cosmos, and yet, paradoxically, almost none of the individual stars or planets caught up in it ever actually touch one another. That paradox becomes even more vivid when we zoom in one more level, down to the scale of individual galaxies colliding. Because this is a story that hits close to home. Quite literally, because it's the story of our own galaxy, the Milky Way, and its looming rendezvous with its giant neighbor, Andromeda. For over a century, since astronomers first measured Andromeda racing toward us at more than 100 kilometers per second, the story seemed simple and almost fated. In roughly 4 to 5 billion years, the two galaxies would slam together in a spectacular collision, eventually merging into one giant elliptical galaxy that some have nicknamed Milkomeda. NASA even produced detailed visualizations of exactly how this would unfold. Tidal tails of stars stretching across the sky, the familiar disk of the Milky Way warping and distorting beyond recognition. It became one of the most repeated facts in popular astronomy. But in June of 2025, a team of researchers led by Till Sawala at the University of Helsinki, using the most precise motion data yet from the Hubble and Gaia space telescopes, ran extensive new simulations incorporating the gravitational influence of our other nearby galactic neighbors, including the Triangulum Galaxy and the Large Magellanic Cloud. And their results genuinely upended the old certainty. They found there is only about a 2% probability that the Milky Way and Andromeda will collide within the next 5 billion years, contrary to the previous assumption that a collision within that time frame was essentially guaranteed. Instead, when you extend the window out to 10 billion years, the odds settle at roughly a 50-50 chance, essentially a coin flip. As one of the study's co-authors, Carlos Frank, put it, we now know there's a very good chance our galaxy may avoid what once seemed like a scary, certain destiny. The subtle gravitational tug of our smaller satellite galaxies, previously left out of the models, turns out to matter far more than anyone expected, sometimes pulling the Milky Way's path away from a direct hit, and sometimes nudging it closer, depending on the exact configuration. It's a beautiful example of how science refines itself. The old prediction wasn't wrong because the underlying physics was flawed, it was incomplete, missing pieces of gravitational influence that only became measurable with newer, sharper instruments. And there's more precision still to come. Researchers are anticipating new data from the Gaia mission that should further refine Andromeda's exact sideways motion across the sky, potentially tightening these odds even further in the coming years. But suppose the coin flip does land on collision. What would a galaxy merger actually look like up close? Just as with galaxy clusters, the individual stars themselves would almost certainly not collide. The distances between stars, even within a busy galaxy, are so enormous compared to the stars themselves that a direct stellar collision during a galactic merger is exceedingly rare. If you shrank the Milky Way down so that the sun were the size of a grain of sand, the next nearest star would still be kilometers away. Two galaxies can slide through each other, stars weaving past stars without a single direct impact. What does change, dramatically, is the shape of everything. Gravitational tides would stretch both galaxies into long, glowing streamers, flinging some stars into intergalactic space entirely while pulling others into wild new orbits. Vast clouds of gas, which are far more spread out, and more likely to interact than stars, would collide and compress, triggering intense bursts of new star formation, lighting up the merging galaxies with waves of brilliant, short-lived, massive stars. And crucially, deep at the centers of both galaxies lie supermassive black holes, and over time, as the two galaxies settle into a single merged structure, these central black holes would slowly spiral toward each other, drawn together by the very fabric of space and time, until eventually they too would merge. As researchers who study this have pointed out, the collision with Andromeda, even if it happens, is far less dangerous to us personally than the eventual death of our own sun, which will make Earth uninhabitable long before any galactic merger could ever threaten it directly. Which brings us to the final, most extreme layer of this story, the actual merger of two black holes, the point where collision stops being a metaphor for gravitational rearrangement and becomes something genuinely, violently real. Unlike galaxies or gas clouds, black holes have no surface to graze past, no diffuse edges to slip through unscathed. When two black holes spiral together and finally merge, they collide completely, and the result is one of the most extreme events physics allows. In July 2025, the LIGO-Virgo-Cagra collaboration announced the detection of a gravitational wave signal named GW23123, and it immediately made history as the largest, most massive black hole merger ever directly observed. The event involved two black holes, one about 100 times the mass of our Sun, the other about 140 times the mass of our Sun, merging together into a single black hole roughly 225 times the Sun's mass. What makes this discovery especially remarkable is that both black holes were also spinning exceptionally fast, making this not only the most massive binary black hole merger ever seen, but also the fastest spinning one confidently detected through gravitational waves. Their masses placed them right at the edge of, or even inside, what physicists call the upper mass gap, a range where black holes theoretically shouldn't be able to form directly from a single collapsing star. That mystery has led scientists to suspect that these black holes might themselves be the products of earlier mergers, black holes born from black holes, hinting that they may have formed in extraordinarily dense stellar environments, like the crowded core of a star cluster or the swirling disk of material around an active galactic nucleus. The physical violence of an event like this defies easy comparison. In roughly a tenth of a second, an amount of energy equivalent to several times the mass of our Sun was converted directly into gravitational waves, ripples in the very structure of space and time, radiating outward in all directions at the speed of light. For that brief instant, the collision briefly outshone, in terms of pure power, every star and galaxy in the observable universe combined, though not in visible light, since black holes emit none, but in the pure, invisible currency of space-time distortion itself. These waves crossed billions of light years of cosmic distance and physically stretched and squeezed the fabric of space here on Earth by an almost unimaginably tiny amount, smaller than the width of a proton, yet still detectable by the extraordinarily sensitive laser instruments of LIGO. And this may only be scratching the surface. Beyond individual cataclysmic mergers like GW23123, astronomers using arrays of pulsars scattered across our galaxy, acting essentially as a galaxy-sized gravitational wave detector, have found evidence of a persistent, low-frequency hum permeating all of space, a background murmur of gravitational waves thought to be produced by an enormous, unseen population of supermassive black hole binaries, orbiting each other at the centers of galaxies throughout the universe, slowly, patiently, spiraling toward their own eventual mergers over cosmic timescales. It's a haunting thought that hidden within the quiet darkness between galaxies, an entire orchestra of black hole collisions might be playing out constantly, a background rhythm to the universe that we've only just learned how to listen for. So, what happens when the largest objects in the universe collide? The honest answer is that it depends enormously on what you mean by largest, and the deeper you look, the more the story surprises you. The truly biggest structures we know of, sprawling superclusters like Quipu, are so loosely bound that they mostly won't collide at all, drifting apart faster than gravity can pull them together, victims of the universe's own runaway expansion. The largest structures that are gravitationally whole, the galaxy clusters, do collide, and when they do, it's the most energetic event physics has witnessed. Since the birth of the cosmos, and yet the individual stars and planets caught inside barely notice, sliding past each other through gulfs of empty space. Galaxies, too, can merge in slow, majestic, million-year-long dances that reshape everything without a single star ever touching another. It's only when you drill all the way down to the black holes themselves that collision finally means what we instinctively picture: total, complete, and violent union, releasing more raw energy in an instant than entire galaxies produce in their stellar lifetimes. There's something almost poetic in that inversion. We often assume that bigger means more powerful, more dangerous, more catastrophic. But in the universe, it's often the smallest, densest points, not the sprawling giants, where the truly extreme physics happens. Perhaps that's the real lesson buried in this question. The universe's grandest structures are, in their own way, gentle giants, vast and majestic, but too diffuse to ever truly clash. It's in the tightest, darkest corners, where matter has been compressed beyond recognition into black holes, that the universe reveals its capacity for genuine space-time shaking violence. And somewhere out there, right now, invisible to our eyes but not to our instruments, that violence is happening, ripples spreading outward from collisions we're only just beginning to learn how to hear.